Atoms were the foundation stones of the universe. Lord Kelvin, practical English genius, who systematized knowledge of mechanics, electricity, and heat in formulation of the laws of energy. Mendeleev, the Russian teacher, discoverer of the periodic system of the elements, who opened new vistas of atomic knowledge. Röntgen, German professor, whose discovery of X-rays provided for science a revolutionary tool. Becquerel, the French experimentalist, who discovered the phenomenon of radioactivity. Max Planck of Germany, who established the law of radiation, which led to the theory of quanta and modern understanding of the electronic structure of matter. Truly the parents of the future science of nuclear physics were the French team of Pierre and Marie Curie. From them came realization that the atom has a core or nucleus, quite different from the shell of the atom. It became apparent that the nucleus is governed by different laws of physics. Concentrating in the atomic field were great laboratories like the Cavendish Laboratory of Experimental Physics at Cambridge, England, fount of so much advanced knowledge in atomic science. Here worked Sir J.J. Thomson, who in 1897 discovered the electron, and his pupil, that giant of atomic exploration, Lord Rutherford, from whom first notions of the proton came, and who discovered and named the proton. He was the first to disintegrate the nucleus. He established the character of radium emissions and suggested what the true nature of the atom might be. Max von Laue of Germany interpreted the crystalline structure of matter, clue to the secrets of atomic structure. In 1905, Albert Einstein wrote the mass energy conversion equation. This was a great milestone, a great victory of man's genius. Einstein unlocked a treasure trove for experimenters. He provisioned them for vast new marches into the unknown. A student and co-worker of Lord Rutherford, Sir James Chadwick, in 1932, discovered the third fundamental particle of the atom, the neutron, an ideal projectile for splitting the nucleus. Final clue to the discovery of the neutron was supplied to Chadwick by Frederick Joliot and his wife, Irene Curie-Joliot, who had observed a peculiar property of the radiation emitted when beryllium is bombarded with alpha particles. Millikan measured the charge of the electron, and Anderson discovered the positive electron and the mesotron. Enrico Fermi, outstanding Italian physicist, in 1934 bombarded uranium with slow neutrons and created new elements. One of the best devices for producing new isotopes and new elements is the cyclotron, developed by Lawrence of the University of California. Niels Bohr, Danish physicist, is chiefly responsible for the planetary conception of the atom. First to probe the atom with X-rays was the young British physicist Moseley, who established atomic numbers of the elements through studies of their X-ray spectra. Deuterium, or heavy hydrogen, was discovered by Harold C. Urey and a group of associates. Rutherford called it one of the most important discoveries of the century. Heisenberg, collaborating with others in Germany and Denmark, elucidated the structure of complex atoms and announced the principle of indeterminacy of physical measurements. 1938 brought the startling discovery of fission of the uranium nucleus by neutron bombardment. Leading names in this research, carried on in Germany, were Dr. Otto Hahn and Dr. Fritz Strassmann. Lisa Meitner, working at Copenhagen, soon demonstrated that fission of the nucleus was accompanied by release of enormous amounts of energy. Allied scientists recognized that uranium fission was of far-reaching and practical importance, not only because of the tremendous release of energy with a single nuclear fission, but because of the possibility of self-sustaining chain reactions. Swiftly, scientists in the United States confirmed the German discovery. This was accomplished in January 1939. At this juncture, Allied interest in the military possibilities of atomic weapons began. Quietly, a military race was started. Free interchange of scientific information came abruptly to a halt. In the fall of 1939, Dr. Einstein wrote his now famous letter to President Roosevelt explaining the urgency of work on uranium fission. Roosevelt, a man of action, moved swiftly. An advisory committee on uranium was appointed. At the Bureau of Standards, the committee first met on October 21st, 1939. 8 recommendations were made to the President. Mentioned as possibilities were atomic power and an atomic bomb.
time was short. Great Britain and France were already at war. The inevitable entry of the United States was accepted. Fear of German research stimulated activity in the United States and in England. One reason for the decision to concentrate forces against the Germans was recognition that German scientists could produce weapons of great devastation. The scientific competence of this foe was never doubted. Comparable peril from Japanese science did not exist. Early in the war, Allied intelligence had disclosed that Germany was increasing production of heavy water in the famous Norwegian hydroelectric plants at Ryukon and Vemork. These plants also produced vitally needed ammonia. The Nazi war regime was using heavy water for uranium research and also to improve the financial position of the Reich. Just before the invasion of Norway, the French government had purchased virtually the entire world stock of heavy water. At the time of the fall of France in June 1940, Joliot had sent 165 liters of the water to England. This heavy water, which twice had nearly fallen into German hands, permitted vital experiments to be conducted later at the Cavendish Laboratory, research which aided the Allies immeasurably. In the winter of 1942-43, with heavy loss of life, patriotic Norwegian saboteurs and British commandos wrecked equipment in the plants, and the Army Air Force did a neat job of strategic bombing which left the plants crippled. Meanwhile, a ferry carrying heavy water bound for Germany was sunk. German scientists made great strides in nuclear research, just as they had in aerodynamics and in rocket warfare. Their conception of an atomic bomb was an atomic pile guided out of control. They worked hard, but when the war ended, they still had not succeeded in creating a self-sustaining pile. They overlooked the use of a three-dimensional lattice and the role of fast neutrons in achieving detonation. They produced no plutonium. When Strasbourg fell, German atomic documents were recovered and a few physicists captured. Strategic circles then learned that vaunted German progress had lagged behind our own. News of the bomb drop at Hiroshima was a shocking surprise to intern German physicists. They had believed that construction of an atomic engine must precede a workable bomb, and that without German help, no bomb could be built. In June 1940, President Roosevelt organized the National Defense Research Committee. The Uranium Committee became a part of this group, reporting to Dr. Vannevar Bush. As Dean Pegram returned from a survey of British atomic research, Dr. Bush and the National Defense Research Committee determined on an all-out effort to develop an atomic bomb.
Chadwick and the other physicists agree entirely with us that given pure uranium-235, we can make a bomb that will work.
I'm going to see the president tomorrow. I'm sure that he will agree that the job has got to be done and that we'll get the support that we need.
Pearl Harbor had plunged the United States into war. An effective partnership of scientists, engineers, industrialists, and the military was formed. Work in universities and independent research laboratories was coordinated. Manhattan Engineer District, a new branch of the Army's Corps of Engineers, was established to administer work on military uses of uranium. Major General Leslie R. Groves was placed in charge of all activities of the project. The end of 1942 was a critical period. On December 2nd, the first self-sustaining chain-reacting pile was successfully operated at the University of Chicago. On that day, without fanfare, far from the field of battle, the atomic age loomed upon the threshold of history. This success galvanized authorization for construction of the great Clinton diffusion plant at Oak Ridge, Tennessee, and the giant plutonium-producing plant on the Columbia River at Hanford, Washington. Now the task assumed tremendous proportions in expenditure and effort. The expense was staggering, the obstacles gigantic, the possibility of failure ever present. Development of the atomic bomb eventually cost $2 billion. Scaled against the cost of total war, this figure loses magnitude. When the second bomb was dropped, the war had cost the United States $286,748,000,000. the daily cost of continuing the war was roughly $213 million. The plants at Hanford and Oak Ridge took form rapidly. The Oak Ridge pile started operating on November 4th, 1943. The first of 3 piles at Hanford began operation in September 1944. The Oak Ridge plants were designed to concentrate U-235 by different methods. U-235 is one of the 5 known isotopes of uranium. The Hanford plant was the source of that new man-made element, plutonium. Activity progressed at fever pitch. Problems, ugly, difficult, seemingly insuperable problems appeared. By dint of concerted effort, they were solved. As we look back now, what was accomplished appears as day-to-day miracles on a production line. At the time, it was work, 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 and more work. The first atomic bomb was assembled at Los Alamos, a secret laboratory in New Mexico. Scientific equipment was first obtained from universities and research projects. New equipment, built to specification, soon made Los Alamos the best-equipped physics laboratory in the world. When Dr. J.R. Oppenheimer arrived in March 1942 to take charge, he began to surround himself with a galaxy of outstanding scientific stars. The roster included many of the recognized leaders in modern-day physics and technical specialists from all parts of the world not then under enemy control. Sir James Chadwick headed an array of top British physicists at Los Alamos, and this group made invaluable contributions to technique and design. Professor J.D. Cockcroft, first to split the lithium atom in 1932, was another British consultant who gave vast help. Niels Bohr, one of the modern giants in physical science, made himself available after his escape from Denmark via Sweden. From Los Alamos came the bomb design and treatment of many theoretical problems. Measurements of the nuclear constants were refined and extended. Methods for purifying materials to be used were developed. Finally, in July 1945, a practical bomb was completed. This, briefly, is the history of the development of the atomic bomb. It was the harvest of science from many centuries, harnessed to the concentrated efforts of the greatest gathering of scientific brains ever assembled in one group with a single objective. When these men on July 16, 1945, exploded the first bomb in the Trinity test at Alamogordo, they were not releasing upon an unsuspecting world a weapon of unknown potentialities. The power of the bomb had been predicted within close limits by careful calculations, and while the explosion definitely was greater than the average expectation, it did remain within the calculated limits. Military weapons dependent upon nuclear energy were now and henceforth an inescapable reality. Energy released by explosion of one atomic bomb of the type used at Nagasaki is roughly equivalent to that generated by exploding 20,000 tons of TNT. 20,000 tons. 40 million pounds of TNT would fill 2 good-sized cargo ships. Yet, all this energy was contained in one bomb. Nor is this all. In the early stages, the explosion reaches a temperature unmatched except inside the stars. The light radiated from its surface can produce burns well beyond the dangerous range of blast alone. During the burst, there are radiations traveling at tremendous speeds and invisible to the eye that reach even those protected by tile and concrete walls or metal shields. These are gamma rays and neutrons that penetrate and kill with insidious efficiency. Danger persists after the blast has died away. Lethal materials, fission products, and the dregs of the bomb float about over the debris and beyond it. These exist in quantities equivalent in radiation to hundreds of tons of radium. Where they settle is death. These radium-like products give the atomic bomb its greatest deadliness. Under favorable conditions, they may last years or even centuries in dangerous amounts.